you have done this classwork during the break. What you have to do here is simple, very simple. Instead of A, I have given you the hint E. On the right hand side for E, there is a. For A, you have to just put J omega mu 0 P GR. So once you put that, and then with simple algebraic and vectorial manipulation, you will get the equation for E. Now we have got two equations, one for H, one for E. In both the equations there is GR, and on the GR there is a vector operation, gradient vector operation. So grad GR, GR is a scalar, and gradient vector operation grad GR. So we need to know the nature of grad GR. What is grad GR? That we need to find out to find explicitly what is H, what is E. So let us do that. So let me give you a note on grad GR. GR or the GR is the Green's function. Green's function is of the form exponential minus jkr divided by 4 pi r. This we have already seen earlier when we discussed about potential. So this we have seen. So this is the Green's function. Now on this depends, if you look at this Green's function, D depends only on r. There is no dependency on phi, or there is no dependency on theta. Therefore, when we consider the gradient operation, only the on the r part will be there. The other part, theta cap and phi cap, they will not be, or dou by dou theta will be 0, dou by dou phi will be 0. They will not be considered. Therefore, del operator for the Green function is equivalent to r cap dou r. Dou r means dou upon dou r, partial differentiation with respect to r. So partial r. Now I'll find out what will be the gradient G. Gradient G will be r cap dou r operating on exponential minus jkr by 4 pi r. Now you can differentiate this easily. This function can be easily differentiated. R cap remains as it is. Then inside, when we operate on the numerator, it will give us minus jk exponential minus jkr by 4 pi r. Then when we operate on the denominator, that will give us minus exponential minus jkr by 4 pi r square. So on these two differentiations gives us these two terms. Now if you look at these two terms, what is common is exponential minus jkr by 4 pi r. So let us take that common outside. So this becomes grad G is equal to minus r cap, because minus is also common, minus 1. So minus r cap whole into jk plus 1 by r, that into exponential minus jkr by 4 pi r. So that my exponential minus jkr by 4 pi r is equal to G. Therefore we can write it as minus r cap operating on jk plus 1 by r, that into gr. So grad gr is equal to this much, minus r cap into jk plus 1 by r into gr. So this is something that we must note and use this grad G in the expressions for the fields. Now let us find out the fields using this. Okay. And the first field that we are interested is mostly the electric field. Now electric field is equal to E is equal to 1 by j omega epsilon 0 into curl H. From where we get this, that I hope you remember that curl H is equal to j plus dou d by dou t. In the source free region, j is equal to 0. So curl H is equal to dou d by dou t. From that we get dou d by dou t is epsilon 0 dou e by dou t. Dou e by dou t is j omega e. So we are using that. E is equal to, now from that you can find out E is equal to 1 by j omega epsilon 0. Correlate, this comes from the Maxwell's equation for time harmonic field. Now curl H we know H is equal to minus j omega t cross grad of gr. So correlate will be 1 by j omega epsilon 0 will remain as it is for E. Then for correl H we will write j omega, let us take that part as common. Then delta cross for H we will write P cross grad of GR. Now grad of GR, for that we will use this part. The other part for grad of GR we will use minus r cap jk plus 1 by r GR. That is for grad of GR. So if we put that, using this we will get E is equal to 1 by epsilon 0. From where we get 1 by epsilon 0? Because in the numerator there is j omega, denominator there is j omega, they cancel out. So 1 by epsilon 0. Then whole into P into this comes from the back cap rule. A cross B cross C is equal to B A dot C minus C B dot A. So use that. Using that we get this much. 1 by epsilon 0 into this. So these two terms we get from that. Using that we will get another. So that gives us the H E field. Then H field is minus j omega P cross grad GR. So that GR we know what is GR, minus r cap jk plus 1 by r into GR. So use that here for grad GR. So that will give us H is equal to j omega remains as it is. Then P P cross grad GR. So P will be P cross r cap. In the grad GR there is this term common, jk plus 1 by r. This is constant term that does not depend on P, so that we will take outside. Then what is inside is P cross r cap, that these two are vector, that is operating on GR. So GR remains as it is. Now what is E? E is equal to 1 by j omega epsilon 0 curl of H. So the electric field is this. Curl of H we can find out. Okay. And so if we find out curl of H, 1 by j omega epsilon 0 remains as it is. Then this will be H we already have found out. So curl of H will be curl of j omega into jkr plus 1 by r, that is the H part, into P cross r cap into GR. So what we have done is, for H we have put j omega into jk plus 1 by r into P cross r cap GR. And now let us write that in this manner. E is equal to 1 by epsilon 0. Okay. And now E is equal to 1 by j omega epsilon 0 into the last line you see. If you look at the last line, the j omega term is in the numerator as well as in the denominator. So we'll cancel out the j omega term from the numerator and denominator. Once we cancel out the j omega term from the numerator and denominator, we are left with 1 by epsilon 0 or del cross jk plus 1 by r into P cross r cap into GR. Now let us rewrite that. That we can rewrite as 1 by epsilon 0 r cap dou r, which means it is operating on or differentiation with respect to r of jk plus 1 by r into P cross r cap GR. From where we get this dou r cross? This is because delta, when it is independent upon theta and phi, delta is equal to r cap dou r. So we are using that part only. So that is using that we get this equation. Now this will be 1 by epsilon 0 will remain as it is. Jk plus 1 by r, let us take that outside. Then do the vector triple product part. If you do the vector triple product part, we will get this equation. 3 r cap into r cap dot p minus p by r, that is operating on GR, plus k square by epsilon 0 r cap cross p r cap p cross r cap into GR. This I will leave as a homework for you to prove. Prove this as a homework. And if you cannot do this as a homework, then we'll see. But this I leave as a homework for you. Now, change. After this, once we have done this, what we have done is we have located the dipole at the point at the origin. So r dash is equal to 0. Now let us change the location of the dipole to r0. So from r dash is equal to 0, let us move it to r0. So PR will be P into delta Q r minus r0. If you shift it by an amount of r0, r becomes r minus r0. So PR will be P into delta Q r minus r0. Then r cap will approach capital R cap. Capital R is equal to r minus r0, that we know. And accordingly G small r will be G capital R, which means the fields are unaffected. If we are changing R0, R to R0, the fields are unaffected. Fields are not affected by changing R to R from any point to another point R0. The fields remain unaffected. Now you can see why fields remain unaffected. The reason is G small r is equal to G capital R. Therefore, the fields remain unaffected. Now, let us consider the physics part, a little bit of physics for the Hertzian dipole. This is, let us start with the static field. K is equal to 0. As you know, K is equal to omega root over of mu epsilon 0. Mu is not 0, epsilon is not 0. Therefore, K is equal to 0 indicates omega is equal to 0. Omega is equal to 0 means frequency is 0. Frequency is 0 means it is a static field. So, K is equal to 0. The first condition is K is equal to 0. That is what we are considering. So, if K is equal to 0, the field is static. If the field is static, there will be no radiation. So for all K, we will put J, K is equal to 0. Now E is equal to, there are two terms. In the second term, it is a K square is multiplied, so the second term goes to 0. In the first term, there is a JK term, so that goes to 0. So what is left is 1 by R into 3 R cap into R cap dot P minus P by R into GR. So that is 1 by R square term. There will be in the denominator 1 by R into 1 by R square. Since there is R square in the denominator, that is not a radiating field. A radiating field is of the form, in the denominator there will be only R variation. R square and R cube variation will not be radiating. Therefore, K is equal to 0 gives you static field. Static fields do not radiate. So there is no radiation. Then K is not equal to 0 gives us radiated. So let us consider the radiated fields. In the radiated fields, we consider only the terms which are decreasing as 1 by R. Other terms are not contributing. Now, there will be two types of radiated fields as we have discussed earlier. That there will be a near field, there will be a far field. In the near field, the energy is stored. In the far field, energy is dissipated or energy is propagating. Now, the near field, in this case, it is also non-radiating because it is storing the energy. This will drop faster than 1 by R. Now, wait. So what do you mean by this? Look at the electric field expression, which is written in the red letters at the top right hand side. There are few terms. The first term is 1 by epsilon 0 Jk into a term which varies as 1 by R. Then the second term is 1 by epsilon 0, then 1 by R into 1 by R, which is 1 by R square term. So that is, the second term is dropping faster than 1 by R. It is dropping as 1 by R square. It is dropping faster than 1 by R. So the second term is a near field term. Then the third term, you can see in the third term we have r cap cross P cross r cap into GR, which means that is a term which is varying as GR is 1 by R, then we have r cap, so that is dropping as RQ. So that is also not contributing to radiation, that is a near field term. So the second term and the third term are near field term. The first term is contributing to the radiation. Now, if you have such a dipole, which is called a Hertzian dipole, how do you realize this practically? This is actually a fixed research dipole, but practically we try to realize something which is very close to this, although it is not exactly same, which is very close to this. So that we do using nanometers or so what we do is we take a dielectric probe, and the tip of the dielectric probe is so thin that we make so thin that it is of the nanometer size. So we take nanometer size dielectric tips. So this will be constructed from a tapered fiber. Let's take a fiber, dielectric fiber. So taper it, so it will have a larger diameter at one end. Then that diameter gradually decreases as you go on increasing the length of the fiber. The diameter decreases to a nanometer size. So that is what is tapering. So taper it, that will act as a tiny dipole or a small dipole. Which now what we will do with this? This can be used to probe the evanescent modes. What is evanescent mode? Non-propagating. Evanescent means non-propagating modes. As we have discussed now, there are two types of field. One is radiated field, which is propagating field. One is near field, which is non-propagating field or evanescent field. So such a dipole or such a dielectric tip or a nanometer size dielectric tip will be able to measure or find out or probe the evanescent field or the near field from any object. This will result in a dramatic increase by factors of 10 or factors of 100 of the resolution of the optical microscopy. When you are using a optical microscope, the resolution will increase because we are now able to see what is in the near field. So near field part is also contributing. Along with the optical part, the near field part is also contributing. That increases the resolution. So this goes beyond the Rayleigh diffraction limit, and this goes down to atomic level of or atomic scale of resolution. So this is one application of Hertzian dipole that usually we use in microscopic study. When we probe using a Hertzian dipole, we increase the resolution. This is one application. This is actually, therefore, on this near field probing is important in new areas of near field scanning, what we call near field scanning or probing. That is why it is important. Now, we will consider our interest in the antenna community is mostly in the radiated field. So we will consider the radiated magnetic field and the radiated electric field. HRAD or the radiated magnetic field is given as J omega into Jk into P cross R cap GR. So how do you get this? The simple thing is H is equal to this, we have found out H is equal to j omega into jk plus 1 by r into p cross r cap gr. Now from that we will take only the part which is varying as 1 by r. Now if you consider the second term which is multiplied by 1 by r, that is varying as faster than, or that is dropping faster than 1 by r. Therefore that is dropping as 1 by r square, 1 by r cube, etc. So that part we neglect. So what is left is j omega jk p cross r cap gr. So therefore h rad is equal to j omega jk p cross r cap gr. Now that we can write as k square j omega jk. J is minus 1 omega into k. Omega, as you know, omega is equal to as you know, k is equal to omega into root over of epsilon 0 mu 0, or you can say omega is equal to k by root over of mu 0 epsilon 0. So now omega k we can write as k square by root over of mu 0 epsilon 0. Now what is mu 0 epsilon 0? That we can write as root over of mu 0 by epsilon 0 into root over of epsilon 0 into root over of epsilon 0. Now root over of mu 0 by epsilon 0, that is called eta 0. So the numerator now becomes root over of mu 0 epsilon 0, that becomes eta 0 into epsilon 0. So right hand side is k square by eta 0 into epsilon 0. Now look, j into j is minus 1. So what we can do is a cross b is equal to minus b cross a. So minus 1 into p cross r cap, that we can write as r cap cross p. So k square by eta 0 epsilon 0 into r cap cross p into gr. Gr is equal to, as you know, exponential minus jkr by 4 pi r. So that part, that is the H radiated magnetic field is given by this expression for a Hertzian dipole. Then the electric field will be E rad, that is k square by epsilon 0 into r cap cross p cross r cap into gr. This expression also we have seen that we can rewrite as k square by epsilon 0 r cap p cross r cap. Then for g we will write exponential minus jkr by 4 pi r. From where we got E rad, that we have already seen what is the expression for electric field. From the expression for electric field, we just drop the terms which are falling faster than 1 by r, which means 1 by r square and 1 by r cube term. Those terms we drop, and from that we get what is E rad. So radiated field and radiated H field and E field we found out. Now how do you relate these two? Is there any relationship between the radiated H field and E field, magnetic field and electric field? There is a relationship. Do one thing, multiply on the H rad field, on both the sides multiply eta 0. So that will make eta 0 H rad will be equal to r cap cross E rad. So that we can write. So from that we can get it, eta 0 H rad is equal to r cap E rad. So that is the relationship between these two. Then we'll now take a break here. After, when we come back from the break, we'll consider how we got Hertzian dipole and what is these P cross r cap. Those terms we'll try to drop down after the break.